Day 2, limits. Finding limits using graphs and properties of limits will be what part 1 will focus on. So we've been talking about what does it mean to get closer and closer. We've been looking at as x gets closer and closer to a certain value. Fix that. As x gets closer and closer to a certain value, say as x gets closer to and closer to 2, what does y get closer and closer to? Okay? Closer and closer is really just talking about a qualitative idea. And if we want to talk about a quantitative idea, we would need to use some other variables, let's say. One variable is delta, and another variable, epsilon. Just looking at this graph to the right, delta is the distance or the interval surrounding the x value we want to get close to. So we want to get closer and closer to c, which means delta has to get smaller and smaller and smaller. Okay? If this distance represents delta, the interval surrounding c, and we go up to our graph, we notice that we get an interval in y surrounding our limit value. So this would be L plus our epsilon, and this would be L minus our epsilon. Okay, so a limit is going to exist if delta gets closer and closer to 0. Therefore, our x is getting closer and closer to c, and consequently our y value for our limit will get closer and closer to L, because as delta decreases, our epsilon is also going to decrease, moving our limit value closer to L. I'm not going to go into the formal definition of the limit using delta and epsilon, but we will take a look at a few graphical examples. So here we have the limit of f of x as x approaches 2. Here's our function, defined as a piecewise function, 4 minus x, for x not equal to 2, and 0 when x does equal 2. So there's a hole in our graph at the point 2, 2. So the limit says, what is the y value as x gets close to 2? So if I move x closer and closer to 2, what's happening to my y values? They are getting closer and closer to 2. All right, the second graph is a parabola, again, but defined as a piecewise function. So x squared plus 2 when x is not equal to 1. Again, there's a hole in my graph at 1, 3. I'd like to find the limit as x gets closer and closer to 1. So I'm going to look on my graph. What's happening if I walk along my graph and get closer and closer to an x value of 1? My y value gets closer and closer to 3, even though my y value is not defined to be 3 when x is 1. All right, here we have the graph of the absolute value of x minus 5 over the quantity x minus 5. The function graph looks like y equals 1 for x greater than 5, and y equals negative 1 for x less than 5. Now in the first two examples, the y value on the left and the y value on the right were the same. The y value on the left, the y value on the right, we were approaching the same number, I should say. Okay? Here in this graph, the y value is approaching -1 from the left of 5, but +1 from the right of 5. So the left-hand limit is -1, but the right-hand limit is +1. The only time a limit can exist is if the left-hand limit and the right-hand limit are the same. So we're going to say this does not exist. Okay, the next graph is a graph of the function, the rational function 1 over x minus 3. It has a vertical asymptote at x equals 3. As x approaches 3 from the left, the function approaches -infinity. As x approaches 3 from the right, our function approaches +infinity. So the left-hand limit and the right-hand limit are not the same, and we're going to say that this limit does not exist. So limits can be found analytically using some limit rules, okay, some algebraic rules. And I'd like to take a look at just a few of the basic ones to help us understand what they're saying. So here we have a graph of the line y equals 1. Okay, and that, what we're taking the limit of is that function. Okay, I'd like to look at the limit of this function as x approaches 2. So as you approach 2 from the left or 2 from the right, it doesn't matter where you are, you're always going to be on the y value of 1. I can have it as x approaches 7 or x approaches -5. The limit will be 1. So this is a constant function. And so if we look at it in general, the limit of a constant k as x approaches any c value is going to be the constant. Okay, the next rule is the identity rule. Y equals x is the identity function. All right, and remember every point on the y equals x line is x comma y, but it's really x comma x, 2 comma 2, 5 comma 5, -1 comma -1. As x approaches 2, +2, from the left and from the right, the y value on that function is 2. If I approached x equals 7, the limit would be 7. So the limit of the identity function, the limit of x as x approaches c, is always the value that you are approaching because y equals x. All right, the third function is made up of a constant times my function f of x, and in this case my function f of x is x. So it's this function over here, y equals x, but I've multiplied it by a half. Okay, as we approach 2 from the left, the y value on this function is going to be -1. As we approach 2 from the right, the y value will be -1. I could look at that as half of the limit of the function x as x approaches 2. The limit as x approaches 2 is 2, and half of 2. Oh, I apologize, that should be a negative half x. So I'm going to switch that up and call that a negative and a negative. So this will now be negative 1. Okay, sorry about that typo. All right, but we see the limit of a constant times a function is the same as the constant times the limit of the function. All right, here we have the limit of a sum. X and 1 are being added together. So it's kind of like I've added these first two functions together. Okay, I can look at that as the limit. Well, let's look at it graphically first. As x approaches 2 on the left, and x approaches 2 on the right. Our y value is going to approach 3. All right, but I could look at it as x approaches 2 on the function x plus the limit as x approaches 2 of the function 1. All right, this limit is going to be 2, this limit is going to be 1, and if we add them together, we're going to get 3. So the limit of a sum is the same as the sum of the limits. All right, let's see if we can finish these last two. Okay, here we have a difference instead of a sum. Not going to be any different. As you approach from the left, or you approach from the right, our y value is going to approach 1. Again, the limit of a difference is the difference of the limits. So here we'd have the limit of x plus the limit of negative 1. And that's going to be 2 minus 1, or 1. Okay, here we have a product. So I see the two zeros of my function x times x minus x plus 1, having zeros at negative 1 and 0. All right, the limit of a product, I could look and just say, okay, what's going to happen as x approaches 2? Somewhere out here is a 2. My graph is a little bit short here. But when x is 2, I'm going to end up getting 2 times 3, or 6. If I break that up and look at the limit of x as x approaches 2, times the limit of x plus 1 as x approaches 2. Evaluating each of these limits separately, I'm going to get 2 and 3. The product is 6. So the limit of a product is the same as the product of the limits. So in the next video, we'll take a look at using these limits. There are a few more that we'll look at, but we'll also take a look at using these limits algebraically.